Okay, welcome to the deep dive. Let's jump right in. We're looking at a connection you might not immediately think of.
Right.
How does something seemingly abstract, like integration, that symbol from calculus,
Mhm.
become, well, a key tool for measuring something very real, like a forest?
It's a fascinating bridge, really,
Yeah.
between pure math and a very practical industry. We've been looking at a source about integration in forest resource technology,
Yeah.
specifically focusing on calculating total timber volume in what's called a stand.
Okay.
So our mission essentially is to unpack how integral calculus gives foresters the necessary map to figure out how much wood is actually there.
And just so we're clear, a stand, that's basically a specific patch of forest, right? A group of trees they're looking at together.
Exactly, a defined area. The goal isn't just one tree, but the total volume in that zone.
Okay, got it. But still, measuring trees. How does the calculus even, enter the picture? Seems like geometry, maybe?
Well, you'd think so initially. I mean, if trees were perfect cylinders, top to bottom, simple. Area of the base times height. Done.
But they're obviously not. They taper, they bulge, they're irregular.
Precisely.
Yeah.
That's the crux of it. Their diameter changes constantly as you go up the trunk. Sometimes smoothly, sometimes not so smoothly. They're complex shapes, continuously varying.
Okay, so trying to use a simple formula for a cone or cylinder is just, it's not going to be accurate at all, is it?
Not really. It'll give you an estimate, maybe a rough one, but for
Mhm.
real resource management, you need better. And that's where integration becomes indispensable.
Right.
The source really points this out. To get a truly accurate volume for one single complex tree, you need a method that handles that continuous change in diameter.
Okay, so how does integration do that?
The idea is to imagine slicing the tree horizontally, not just a few slices, but conceptually, an infinite number of incredibly thin, like disc-shaped cross-sections, all stacked up.
Ah, okay. Like stacking super, super thin pancakes. Infinitesimally thin.
That's a great way to put it,
Yeah.
exactly. Each tiny pancake or disc has an area, right, based on the tree's diameter at that specific height,
Hmm.
and it has a minuscule thickness. So the volume of one tiny slice is just its area times its tiny thickness. Now, how do you get the total volume of the whole tree?
You'd have to add up the volumes of all those infinite tiny slices from the very bottom to the very top.
Bingo. And that process, summing up an infinite number of infinitesimally small parts.
That is integration, isn't it? That's what the integral sign actually
And
represents.
that's precisely it. Integration is the mathematical machinery designed for exactly this kind of problem, finding a total accumulation when the rate of accumulation, or in this case the cross-sectional area, is continuously changing. It moves way beyond rough approximations.
So it's not just finding areas under curves on graphs like in math class. It's a practical tool for measuring real, lumpy, irregular things like tree trunk.
Absolutely. And why bother with this level of precision? Why not just estimate?
Yeah, I was wondering that. Seems like a lot of effort for one tree.
Well, estimations are okay for some things. But timber is a valuable resource. Think about it. Economic value, planning harvest sustainably, figuring out carbon storage.
Ah, okay. All that depends on knowing how much wood you actually have.
Exactly. Accuracy matters.
Yeah.
Better data leads to better decisions, both economically and environmentally. The source stresses that integration provides the formulation needed for that accuracy. It's foundational.
Right, that makes sense. The stakes are pretty high. It's not just an academic exercise.
Not at all. And then, once you have this robust method using integration to get a precise volume for each tree you measure in the stand.
Then getting the total for the whole stand is just adding up those individual accurate volumes.
You got it. You aggregate the precise individual measurements across the defined area. Integration handles the complexity of the individual tree. Simple addition handles the collection of trees in the stand.
That really connects the dots. So let's bring it back to the listener. If you're maybe wrestling with differentiation, integration in a course right now, what's the big takeaway?
The big takeaway is that these concepts, they aren't just stuck in textbooks, this forestry example. It shows integration as, well, a vital practical tool.
Yeah.
It's used out there in the real world.
In important fields like resource management.
Yes, to get solid, reliable measurements of complex natural things. It gives you the mathematical framework to quantify something as tricky and variable as timber volume across a whole forest area.
It really drives home how powerful math is for tackling real-world stuff, especially things that change continuously.
It really is. It's about understanding the whole by properly accounting for all its continuously changing parts.
Fantastic. So, wrapping up our deep dive here, The key point from the source is that integration is the essential mathematical method. It lets us accurately calculate the volume of individual irregular trees.
And then by summing those up, we get the total timber volume for an entire forest stand.
It's a direct practical application of calculus, showing why understanding these sometimes abstract-seeming concepts really matters.
It truly highlights how mathematical formulation underpins our ability to manage the natural world effectively.
So maybe a final thought for you to chew on. We've seen how integration helps measure irregular trees. Where else in nature? What other systems or resources, maybe involving flows or things spread unevenly or other non-uniform volumes, might also need the power of integration to truly grasp the scale and quantity?